Thanks, everyone. Is this mic on as well or not? No, it's off. Okay, good. If I'm too quiet, I tend to walk around a lot, and let me know. I've been in the field of machine learning for quite some time, I guess even before it was a mainstream field. Did my diploma here in a field called AI, which has a subfield called machine learning. Then did my PhD here on a thing called, we've just talked about it, learning theory. How much can you guarantee statistically from seeing accuracies like click-through rates or judgment agreements on training sets towards future predictions. Worked for 11 years at Microsoft Research in the UK. Anyone here ever played Halo, the video game? So if you ever played Halo online, so that's one of the things I've worked on, the matchmaking system that tries to predict, that learns what everyone's skill level is from match outcomes. Worked for a year at Facebook. I think there was a talk about Facebook ads this morning, so that was the team I was working on. And then since 4 years, I'm at Amazon now on a wide range of problems. So what I wanted to do in the next 20 minutes, sort of two parts. And the first part, look back a little bit what machine learning is, the history of it, and what's the core essence of machine learning algorithms. I think we heard quite some technical details on one aspect or one kind of machine learning, known as deep learning, but there's a broad range of them. Also touch a little bit about what, and then the second part touch upon what applications of machine learning are we having and we're focusing on here in Berlin in the Amazon team. So I'm touching on forecasting, key problem, touching on machine translation that many of you have implicitly seen, probably don't even know that this has been done by machines already. And then hint on an example where you can use visual data, but to predict something that's not so obvious, but interesting. So one of the reasons why machine learning is so important and so critical to Amazon has actually to do with the blueprint of the business model. So the blueprint of the business model says, it's called the virtuous cycles. And at the core, Amazon is not a company that wants to sell books or shoes or compute time or speaker devices or videos. It's about being the most customer-centric company in the world. And there's three simple ingredients that Amazon believes are important for customer experience. One is having the widest, oh, that's not working. Is it? It's not really. One is having the widest selection of products and making it convenient to actually find the right product, whether it's compute time, it's storage, it's a shoe, it's a book, out of this catalog. Because the assumption is if you have a great customer experience, if you have great experience in shopping, you're going to be going there back, so you drive traffic. More traffic drives more sellers because it's a more interesting marketplace. Again, this doesn't matter, it doesn't just relate to book marketplaces or retail marketplaces, but also to compute marketplaces and digital ones. And more sellers lead to more selection. Oops, that was a bit fast. Yeah, and so the second interweaved virtuous cycle says if that first virtuous cycle, having more selection because you have more sellers, leads to more interaction on the platform, you have more data, that should allow you to lower the cost structure, which should allow to lower the prices. And when you now look at, this is too fast, I think I'm going to use my hands. When you now look at what's basically driving customer experience, it's more selection, more convenience, and lower prices. Now you see yellow and you see red arrows. The reason why machine learning is so important is that as traffic grows, as you need more convenience, as you have more selection, the only technology that really allows to take it from manual, which is what Amazon did when it was started, to automatic is machine learning. And so for a lot of the business models, the virtuous cycles, machine learning is a critical technology. So here's a few examples. Forecasting is one, because only with forecasting you can lower the cost structure. Or automating human decision making. Today we're making hourly pricing decisions on 20 million products. You simply couldn't do it with manual effort. Again, this is driving more traffic. Or making the whole convenience of choosing out of a large catalog very simple, and that's recommendation. That's the core of recommendations. Again, while you can do this probably manually for a few 100,000 products, you can't do it for 20, 30, 40 million different products. Now, what is machine learning? And as I said, I started as a scientist. So as a science, it's something that's very young. So most sciences are several hundred years young. Machine learning is only 50, 60 years young. And it's born out of basically the four areas of computer science, because it's about computation that mimics intelligence. It's statistics, because it's the science of translating data or observations that a machine does from the past into predictions of the future. Neuroscience, because the best proxy today we have for intelligent behavior and the ability to extract that is humans. And you can see this a lot in some of the approaches where we try to mimic what the brain does, because the human brain is the best proxy to an intelligent learning mechanism. And operations research. So one thing that came out a few decades after the inception of machine learning is that optimization is very, very core to the mathematics of ML algorithms. It is actually a subfield of AI, even though today it seems the other way around. And from an engineering point of view, the best way that I always think of it is the sort of the sequential execution of 3 binaries that are best visualized on a timeline. So training means everything is sort of taking as input data recorded up to now and putting it into what we might call a model, like the weights of a neural network. Prediction is predicting what is basically using that model to say what's going to happen in the future. So if you do advertising, you'd like to know what's going to happen in the next 15 minutes. Is the customer that I'm going to show him an ad, is he going to click on it or not? If I do search ranking, I'm asking for the next minute. Which of the next few links or search results are you going to click on? If I do search suggestions, I'm actually asking for a future in a few seconds. Like as I throw a drop-down box, which one is the user most likely going to select? If I do forecasting, I'm going 3 to 6 months in the future. If I basically have to decide how many jackets or shoes to buy, I need to know how many will be, in the next summer, next winter season, will actually be bought. It's going into the future. It's the best way to think about it. And then decision making is the first time you actually need to bring business decisions in. What do you prefer most, being overstock or out of stock? Or showing many suggestions to have high accuracy, or showing as few as possible, and that's the first time you actually bring business metrics in, not in the training and predicting itself. From a computer science perspective, what makes a machine learning so attractive is that it reverses the flow that's typically happening in a computer. So in a computer, we typically write programs, and then on a standard CPU, the program is executed against data that's streamed into the registers, and then this produces an output. That's eventually coming on a printer or on a screen or anywhere. Now, with machine learning, you can actually turn the output to an input. So the output that people do, someone that's fairly intelligent, and have a computer compute a program. Because eventually, a neural network is nothing more than a codified program that comes out of the pattern that relates the data to the output. So here's an example. It's actually a practical example from Kindle. And it's actually what we've done. So how many people have a Kindle? Great. How many people know what the X-ray feature is? Whoa. Whoa. Well, if you have a Kindle, try it. Next time you go on a page, there's this X-ray thing in the menu. So the X-ray is a feature where you have a different index, not by pages, but by content, by mention of which character in the story, and then all the characters in the story. So if you take Angels and Demons, then Robert Langdon is a character in that story. Or if you were to take Game of Thrones, then Khal Drogo is a character. So all these characters and all these places, Westeros or Egypt or Pyramids of Gizeh, they've got extracted ahead of time. So the book got pre-processed, and every single mention of any fictional character in the story and every single mention of a place get extracted, so you get an index where you can jump to all the mentions of people and where you can actually see how important are certain characters in certain parts of the book. It just gives you a different way to understand the story and jump back into it. Now, the way that we've done this for the first few hundred books is we literally had hired people that read this text and then they annotated it. So they said this word is the beginning, middle, and end of a mention of a person or a mention of a place. So the data is the raw text, and the output was these markers. Where does the text, where does the mention of a character, of an entity start? The programs that got computed, this is a typical program, are effectively if-then-else programs. Now, in the parlance of machine learning, you'd say it's a decision tree. And there's other ways to represent that. So if you had a network, you could do this with sort of weights that each word has rather than strict rules. But effectively, you have to compute a program that you execute, and we call that prediction. And so that's at the essence. And why is that useful? Well, it's useful because today we can do this for all the books, because we're not doing this lots with people anymore. We do this With uncertainty, meaning for some of the text we can extract it, for the ones where we're not so certain, we cannot extract that, and resultingly have people annotate it to make the system continually better. Now, as I said, the field is pretty young, so let me quickly put that line up and then talk you through it. So when I started, which was around here, and we were already past the first phase, so in the very first phase, the idea was almost like as if you want to build a plane by looking what the bird does. So meaning, if you want to build an intelligent computer, you just look what the brain does. And the brain has a simple compute unit called a neuron. We've got about 3 billion of them, and they are very heavily connected. So this was the time of the 1982 was when the 286 was introduced by IBM, just to give you a sense of the compute power. So we tried as a research field to emulate a 3 billion neuron brain on a 286. Worked to a certain degree, small pictures we could do that, but we hit the wall quite quickly. Any literature you read, learning is actually called adaptation to external stimuli. Data isn't called data, data is called a stimuli. What happened then in the 90s is that a lot of the focus switched towards augmenting human-built rules. And so all these decision tree learning algorithms were primarily invented here. In fact, just as a reminder, most of the deep learning algorithms were invented here, not when they come back here. This also hit the wall because you got very complex rule sets that were, in principle, easy to understand, but with trees, with many forests, you couldn't. The statisticians came into the field in the 2000s, and they introduced a theory of machine learning that would address this very last question that we had in the previous talk. How can I guarantee that the algorithm, that the system makes no errors in the future from just training it right now? And there was some theory called statistical learning theory developed, and the whole question of learning turned into one of, let's optimize cost functions. And a lot of machine learning is still driven that way. Now what happened here, just again as a reminder, this is the foundation year of Google, is people were really starting to apply it in practice. Up to this point, it was a pure research field. And so people really needed to model actual data they observed. And so the idea of modeling forward flows of data became highly popular. And so a lot of the current click models we use for modeling clicks or modeling gamer rankings, they were invented in that period. And then around 2010, the big change that happened is that not just a few handful of large companies, like at the time Google and Microsoft, had large amounts of data that didn't fit on a single machine, but a lot of smaller startups had that. And there was a need to actually make use of it, not throw data away, but learn from all the data that you have. Like we've just heard about how to learn from 80 million images regularly. And so this age of learning as the application of adaptive computing on distributed systems was mainstream machine learning. And then today, about 3 years ago, people discovered that if you marry fast hardware, parallelized matrix computation, GPUs, with the theories from 20 years ago, you actually get highly flexible but adaptive systems that are now trainable on millions, tens of millions of images, and so the deep learning era started. Good. So with that, I have a question. How many systems do you think is machine learning already used at Amazon today? And which ones spring to mind? There's one that should spring to mind right away, because anyone that ever shopped probably saw this little thing that says, recommendation, right? People who bought this book also bought this shoe, or this book. Anything else that you can think of where we already use machine learning? Search, that's right. You type 3 letters and somewhat magically it finds the catalog, just to give you a sense of stuff that's bought by Amazon, is more than 20 million products, and there's many, many more that are done from sellers. There's over 2 million sellers that are selling other goods. So it's not easy to figure out on 3-4 letters what exactly you want. Somehow you get there relatively quickly. Anywhere else where it could be relevant? Forecasting is totally automatic. I mean, in the early years it couldn't be, it was possible to do it manually. Today we rebuy all of these 20 million things almost every day. And so this is an algorithm that predicts and automatically keeps buying to make sure we're not running out of stock, we're not too much overstock. Fraud. Fraud was the second, exactly. Fraud was actually the second application. So recommendation was the first, and fraud detection was the first one that followed this. Basically to make it safe for you to make a credit card transaction and for the seller to make it safe. You know that this seller is actually going to ship you the product, and the seller knows you're going to actually pay for what they just shipped you. There's some that are not so obvious. I think review analysis is a good one. So recently we got to the volume of reviews that are posted that could no longer be manually, so it was already at the time I was at Amazon, manually processed. And the idea here is not to filter out and only leave the positive stuff of a product, but to sort of look at it what's inappropriate. So sometimes it's hate speech that's posted. Sometimes it's just not relevant. It's nothing bad or good. But a lot of reviews would say this stuff shipped in 8 hours, unbelievable, or this stuff needed 4 weeks, unbelievable. And neither of which is nothing wrong with it per se as a language, but it's not relevant to your buying decisions. So that's something that's partway automated by a system that reads the review and makes a prediction: is this relevant to the product described or not? But that's positive or negative, doesn't matter. And then obviously with Echo, we just announced that this week there is speech recognition that we're doing, which is a deep learning model that's actually learning to separate really well what word was said and what was the intent of your question when you asked the question. So let me quickly touch up on the 3 applications as I was mentioning. Forecasting is the first one, and the problem that we had to solve there is one for fashion. And one of the challenges in fashion forecasting is that you have a lot of new products that you don't have past demand, because in contrast to books stick around for more than 1 year. Most fashion is for 1 season only. So there's the sort of summer season, and then when it's sold, you can't, even if you learned a pattern, next summer is a different product. So you need to be able to generalize, not just from pure product, but from the appearance of it. You need to be able to predict styles. The other thing is, fashion has one parameter that is not controllable by you. So books typically come in 1 size, but fashion comes in 11 different sizes, and I can only wear XL and shoe size 45. So I can't pick the shoe size when I'm buying the shoe. But if you are a seller, if you need to order them, you need to order with shoe size. You can't go to the seller to Gap and say, or Bugatti, and order them in an arbitrary size. So you have about 1 order of magnitude reduction of your time series. So if you plot these time series and you think you can just use a textbook or a neural network for this, you have a time series that's for 98% of the time 0. And then it's almost like a spike train. It has a spike. And yet you have to forecast where in aggregate that these spikes will happen. So you actually deal with something which we call very intermittent demand. And so we worked on this one for the last couple of years, and there's a NIPS paper this year that describes the system or the algorithms that we've actually developed to deal with this with these spike series of time series that have very few spikes. So here you see already a super popular product. And you see one thing that we also have to do. Typically, like when you make a prediction, you make a prediction to a point, whether or not something is, how many units, how many individual shoes am I going to sell? When you go up to 6 months in the future, so this is, you think of it as this is 1 December, this is another December, so this is entire years. You cannot be certain, so you have to give a quantile. So you see the green and the blue lines are effectively cuts of the probability distribution in the future. And what makes it hard to even measure success is, in the future, you're just going to have one particular unit, which is the red line. But how accurate was your distribution? As long as it embodies and encompasses the entire number, it's okay, but you want it as narrow as possible. So, having narrow distribution on which the red line is always contained, that's the hard bit. The second application, and out of interest, this kind of system that you see here is actually used now for all the European ordering of fashion. So the second one is machine translation. And so I don't know if any one of you came across this picture, but if you browse the Amazon catalog now, sometimes you see this little box, and this little box, for those in the back row, says this product was automatically translated, and you can kind of get it. It looks very English, but when you read carefully and look at the last word, you see that there's a translation error. That's not an English word. So what we're doing is we translate, and the reason we translate by machine and not by people is pretty simple. In fact, when you think about the flywheel, I talked about the fact that you want as much as possible selection. So if you were to use human translation, so you have people translate product description, then there is a cost per translation. And it's not a good business model to actually sell so this is all products sorted by how much profit over lifetime they make. you should only do this for products that at least pay for the translation, which is this tiny range. If you use machines and you do it good enough to make a purchasing decision, you effectively increase selection. And again, as I said at the beginning, that's one of the blueprints of what we believe makes a good customer experience. So the primary reason is to give that. Now the challenges in the translation is that while you have these generic translation engines that translate from in text you put in text from one language to another in Google or in Bing, they're not trained for the particular corpus of product description, which have sizes in them, which have brands in them. And so we thought, well, this should be easy to do. But one of the problems is, where do you get the aligned corpora? We had some initial aligned corpora, but what are you going to do after you can't just go to most of the training data of these translation systems come from legal text. So in the EU, there's a lot of legal text that is in all the various languages. So one of the challenges was to actually change these translations engines. So this is how they look. That what they do, these translation engines, they effectively weigh two facts, which is how likely, they build a language model, they predict how likely is a translation in the target language, and how likely is each of the elements, the phrases and the words in the source language, a target language. And one thing you need to do if you don't have aligned corpora, then you only have data from this type. So the only thing you can learn from for your translation model, if you want it at volume, is actually that little box you saw up there. Because that little box tells you that at least the one translation that you did show to the user might not be good enough if the person says, or it was good enough. So you really need to actually change the algorithm. So the traditional translation systems measure a lot of the co-occurrence of words and of tokens, but when you really want a lot of data, you need to change the model for that. And the last one, to finish, is an application of computer vision, is in the domain when you try to sell fresh fruits. So what I'm showing you now is a little video that you don't see. For some reason, it only plays here. But you get the. Let me explain what you should be seeing. So what you should be seeing is someone that opened the clamshell of strawberries, and in that clamshell, he takes every single strawberry and he actually checks them, meaning he checks if they are grade A.
Definitely time-consuming.
That's time-consuming. Grade B, grade C, and grade D. This is happening whether you are at Amazon, whether you're at Rewe, Kaisers, Tesco, Walmart. The quality of the produce is actually manually checked, and the reason that has to be checked, also when you sell it, is that in traditional grocery stores, you as a customer are the quality control, because you go to the supermarket and you check it, and then you buy that clamshell, or you check the apple. When you do this online, you actually need to make sure that the quality is as good, at least as good as what you would do. So the idea here was, can we actually learn? Meaning, can we use camera systems to do something like you see in the prototype below, where you show images or a video of a fresh fruit, and you have it predict which quality grade, A, B, C, D, is that particular view of that fresh fruit. Okay, so the good news is you can actually, for some fruits, do it already as accurate as humans do it. But even more interesting is the following experiment. So the next experiment you see shows you, and that's something that was quite funny to do, it shows you 28 strawberries. So this is each a picture of a strawberry, and this is when we bought them from Kaisers and unpacked them, and this is 14 days later. So that's why they get a bit more gray, they actually get a bit furry. Some of these timelines are not fully completed because they were too rotten. And what we wanted to do is not just predict are they good enough or not, but what you actually need when you store them is, when is this point? When are they going bad? Can we predict from the mere appearance here when the fruit goes bad? Because if you can do that, we minimize wastage. And to give you a sense actually, it's a bit of a quiz. Of 100 apples today, because it's a manual process, how many apples that are picked, how many apples do you think will actually be eaten? Meaning, how many apples go to waste because we cannot do this assessment well? That's right, 50% of all fresh fruit that's harvested goes to waste. So part of the goal here is really to actually make this whole agricultural business of selling fresh fruits more efficient. And if you look at these models, what you see here is the test set. So these are the 28 held out fresh fruits, and then using the model, it doesn't predict is it good or bad, but it actually tries to predict the age. How old is the fruit in terms of being freshly grown to rotten? Top left to bottom right. We basically did this test just to validate the model we learned is actually capturing what you might consider the age. Just for the statisticians in the audience, one extra challenge here is, of course, when you get it delivered, meaning day 0, is not when it got picked. So some of them might have already been on the fruit for a little bit of time, some others are not. So you don't really have a baseline, so you have an extra parameter for each fruit to estimate, which is what's the actual age when you started to take the first picture. So I hope in the last 20 minutes I did convince you it's an emerging and scientifically very young discipline. It's actually in the simplest form, whether you use neural networks or use decision trees or use linear separator, nonlinear. It's the science of translating the past. Everything you could record about the past into predictions of the future, and that we've got quite a broad range of problems. Advertising is one that I haven't talked about, forecasting, fresh fruit prediction, or translating text. Thank you.
Thanks a lot, great talk. I'm sure there are going to be one or more questions. Yeah.
Thank you, that was mind-blowing. As people that run engineering teams, I think some of us have this question: how do you breed this culture? Because I'm just thinking here a bit irrationally that of my 100 engineers, I need to convert 90 to data scientists or machine learning specialists, because the sky is the limit as to what you can achieve with that. So how is that imbibed in the DNA of the organization, like Amazon, right?
Yeah, so it's a good question. So the team we have here has two types of roles. So we have software engineers with an ML background, and we have what we call applied scientists. And that applied is very important, that have a bit of an engineering background. So first of all, I think, and it applies a little bit to myself, since I've been 8 years old, my first computer was a ZX81, and ever since then I've programmed. So what keeps the two cultures together is that everyone codes. Now, software engineers build large systems, design the large software systems, and the scientists fill the holes in with the code, right? I think that helps to bridge one of those gaps that you mentioned between engineers and data scientists. So rather than have harsh separation, have a culture where code is the language that exchanges ideas. The second one, I guess the culture of thinking big and the sky is the limit, is really embodying this thinking. If machine learning is the science of turning data from the past into predictions of the future, always ask the question, is this prediction meaningful, and do we have data? Because there's many ideas that people have where we don't really have the data and there's no sensors to record it, or even if it have the sensors, we can't easily 10x or 100x the data. Machine translation was such an example. We can't easily 100x the translation, that costs 100x more. But you can get different type of data, which is a click. So using these sort of principles, data is necessary, so is it available? And is the prediction meaningful or just technically interesting? And repeating this again and again as a thought model are very important for stimulating that thinking.
Hello. So you have shown that you have been working on a lot of different models that mostly cover the traditional problems in e-commerce or retail.
Yeah.
So let me make you a very direct question. So what are you working on right now? So what is your vision for the next 2 or 3 years in e-commerce, in terms of machine learning, of course?
Oh, in e-commerce and machine learning. I thought what I'm working on. So wait, you had asked two questions that give different answers. Do you want to know what I'm working on right now, or do you want to know what the future of e-commerce in 3 years is?
Well, if you can mix both, it would be interesting.
So one of the things that we are working on right now addresses one of the points that was the question just before. What we see is that there is more people that would love to use tools of data science than the tools allow you to use them. Because a lot of the tools on the market today, I think one of the big things that are not so spoken out about deep learning is with frameworks like Theano and Keras and TensorFlow and MXNet, you're basically making it you lower the entry barrier for anyone to build models. Not necessarily to extend it. I think there's few people that can extend the algorithms, but at least you make it very easy for anyone here in the room, leaving this and by this evening having built one model if they have a data set. data set meaning a table of data. That was not possible in the more traditional learning algorithms. Like if you wanted to use a base net, there's no good software library to do that. So what we're working on right now is building models is just one aspect of a life of a data scientist, which is visualizing data at any scale. Visualizing errors of predictions on data to iterate. So what we are working on right now is actually making tools that so far have been locked in for people that needed a master's or a PhD machine learning to be usable by software engineers. That's what we're working on right now. Now that's not answering your second question. I think for the second question, let me venture a guess. I think one thing that I do think becomes more and more in reach is, have you heard about the Amazon picking challenge? So 2 years ago, we believed that we wanted to get a sense, where's the robotics field at? And the task was relatively simple, which is have an arm automatically, tell the arm you need to grasp this. This one is in a shelf, grasp it and put it here. Because when you look in a traditional fulfillment task in e-commerce is also still shipping products, that is a common task. Someone needs to put it into the tote, that it goes into a packet, so it actually goes with the post, with the mail, and arrives on your doorstep. And what's interesting is this was actually harder, much harder than playing football with robots. So a bunch of teams, I think about 20 or 25 teams did participate, so we did the second one this year. And what we were surprised is there was actually the team from Technical University of Berlin that won this challenge. So you got a score for whatever you picked. The harder objects got you more points, and if you picked them and dropped them right, you got more points than picking them and dropping them on the floor, the arm. So a projection, I think today it's still visionary to think that you can fully automate that, but I think in 5 to 10 years from now, given what I've seen of those robotic challenges and where the science is at, and the relevancy of that problem, this might be an interesting area where science meets real world in e-commerce.
Okay, we have a coffee break right after this talk, so I hope Rolf is going to stick around for a few minutes, and feel free to approach him with any questions. I think, a lot of questions to be asked, I think. Okay, see you after the break.